Hello and welcome to Stories of Science. Here, we look back on humanity's long journey to understand the world. The questions, the failures, and the breakthroughs that slowly changed how we see the universe and ourselves. We tell science as stories. The asteroid that shouldn't exist, but refuses to fall apart. If the universe kept a hall of failures, Vesta would probably be sitting right near the front row, with a little tag that says almost made it, almost. But here's the strange part: most cosmic failures are messy, broken, scattered, barely there. Vesta didn't get the memo. It's too intact, too organized, almost like it showed up in the wrong story. Between Mars and Jupiter, there's the asteroid belt. Sounds crowded. In reality, it's more like space junk after a cosmic renovation project. And Vesta, it's the cleanest piece of debris in the entire mess. About 525 kilometers wide, not just a rock. More like a serious contender in a field of fragments. In the right conditions, it can even get close to the edge of naked eye visibility. So it's not invisible space dust. It's more like a faint visitor you could notice if you were paying attention. And then things get weird. Most asteroids are chaotic, irregular shapes. Craters everywhere, like they've been through a long war with nothing but impacts. But Vesta is different. It has layers. A metallic core. A rocky middle. A solid crust. Sound familiar? That's planetary structure, not asteroid behavior. And that's when scientists paused. Because you don't expect a failed rock to behave like a fully trained planet. As the saying goes, that's a horse of a different color. So the question hits harder than expected: how does something this small end up this structured? To understand that, we rewind to the early 1800s. 1801 series is discovered. 1802 Pallas follows. Suddenly, astronomers start thinking, what if Mars and Jupiter once had a full planet, and it blew apart? A cosmic tragedy. A missing world. That idea spread fast, almost like an old legend people wanted to be true. Then comes Heinrich Olbers. Not just a stargazer. A detective of the sky, the kind of person who hears it's impossible and replies, "Watch me." He begins scanning the heavens systematically, looking for fragments of that lost world. And then, on March 29, 1807, he sees it. A steady point of light, not flickering like a star, not random like noise. Just moving with purpose. Bright. Too bright to ignore. He records it. It's confirmed. A new object, Vesta. Named after the Roman goddess of the hearth, warm, domestic, peaceful. Ironically, nothing about it feels peaceful in science. At first, it's just another asteroid. Nothing special. Case closed. But the data refuses to behave. Vesta is too structured, too complete, too planet-like. And that creates a problem. Because if it really is a fragment, then what kind of original world was it carved from? And if that world existed, why don't we see anything else like it? Or worse, what if we misunderstood the entire story from the beginning? In science, as the saying goes, the more you look, the less simple it gets. And with Vesta, the mystery is only just getting started. If you slice into Vesta, you won't find a messy jumble of random rock like you'd expect from a small asteroid. Instead, it behaves almost properly. Thanks to NASA's Dawn mission, which studied it closely between 2011 and 2012, scientists confirmed something surprising: Vesta is layered. At the center sits a metallic core, mostly iron and nickel. Around that, a rocky mantle, and on the outside, a solid crust. Sound familiar? It should. Because that's basically Earth's blueprint. The problem is scale. Earth is over 12,000 kilometers wide. Of Vesta? Just about 525 kilometers. So you're looking at a planet in miniature. And that's where things start to feel off. Because in the usual picture, small bodies are supposed to be simple, cold, broken, loose, like leftover debris from construction work in space. But Vesta didn't get the memo. It's structured, organized, almost like it passed a planetary exam, but didn't graduate. So the question becomes obvious: how does something this small manage to differentiate into layers at all? To answer that, you have to go back to the earliest days of the solar system, around 4.56 billion years ago. Back then, space wasn't calm or tidy. It was violent, hot, packed. A cosmic construction site where everything kept colliding. And inside that chaos, one ingredient mattered a lot: aluminum-26. A short-lived radioactive isotope, but an intense one. In the first million years of the solar system, it acted like hidden internal heating. When trapped inside young bodies, it released energy continuously. And the effect was dramatic. Temperatures rose, ice and rock began to melt, some bodies literally turned into molten interiors. Then physics took over. Heavy elements like iron and nickel sank inward, lighter silicates rose outward. That's planetary differentiation. In other words, Vesta wasn't born structured. It cooked itself, and then reorganized. Like a cosmic baking experiment gone surprisingly right. But there's a catch. Aluminum-26 doesn't last long. Roughly a million years, then it fades out. So only objects that formed early enough got the full meltdown treatment. Vesta just happened to arrive on time. But this is where the tension starts. If Vesta really went through full differentiation, you'd expect a clear, massive mantle layer. Yet observations tell a different story. The mantle signature, especially olivine, a key mineral, is weaker than expected. It's like cutting into a 3-layer cake and finding one layer mysteriously missing chunks. Naturally, scientists weren't thrilled, because this hits a basic rule: conservation of mass. If the mantle was supposed to exist, where did it go? Was it stripped away by impacts, never fully formed, or violently mixed later? There's no single agreed answer. And this missing mantle problem gets even louder when we move to Vesta's southern hemisphere. Because there, the surface doesn't look like geology. It looks like an accident report written in stone. A massive impact basin called Rhea Silvia. A scar so large it dominates almost the entire southern half of the asteroid. If Vesta were an apple, Rhea Silvia would be someone carving out nearly half of it and flipping the inside outward. At the center sits a mountain rising close to 20 kilometers high. To put that in perspective, Mount Everest is about 8.8 kilometers. This one is more than double that. And it didn't form slowly. It was blasted upward instantly during impact. NASA's dawn reconstruction suggests the collision happened roughly 1 to 2 billion years ago. The energy release was enormous, approaching planetary scale destruction. In simple terms, this wasn't a hit. It was a planetary resurfacing event. And yet, Vesta survived. It didn't shatter. It didn't disappear into rubble. It just lost a huge chunk of itself. The debris didn't vanish either. It spread across the solar system, forming what scientists call the Vesta family of asteroids. And here's the more unsettling part. Spectral analysis shows that about 6% of meteorites found on Earth match Vesta's composition, meaning some of the rocks in museums, or even on the ground beneath your feet, may have started there. Far away. In a body that got half its surface torn open. Sounds unbelievable, but the chemistry doesn't lie. In other words, you might have already touched a piece of it, just not when it was still there. But the big question remains. If the impact was that powerful, strong enough to carve out half a hemisphere, why didn't it destroy Vesta completely? By all logic, it should have turned into a cloud of rubble. So why is it still here? Or put more uncomfortably, what exactly allowed it to survive at all? When NASA finally decided to take a serious look at Vesta, scientists were already half prepared for surprises. After all, this asteroid had already raised suspicion once, like it didn't quite fit the role it was supposed to play. But nobody expected the real twist. The closer we looked, the more complicated it became. It all starts in 2007. On September 27, a spacecraft called Dawn launched from Cape Canaveral in Florida. Its mission sounded poetic: travel back to the time capsules of the early solar system. But the journey itself was anything but poetic. Dawn used an ion propulsion system, very low thrust, extremely efficient, painfully slow. So instead of blasting off like a rocket hero, it basically crawled through space like a patient mechanical snail. And honestly, not everyone believed it would work. At the time, ion engines were still considered experimental. But as the saying goes, slow and steady wins the race. And Dawn proved it. After years of orbital adjustments and even a gravity assist from Mars in 2009, it finally arrived at Vesta in July 2011. For the first time in history, humanity got a close-up view of an object discovered back in 1807. And the first images came back, a little unsettling. Because Vesta wasn't simple. It wasn't even close. Dawn was equipped with three main tools: high-resolution cameras to map surface details down to tens of meters, a gravity experiment to reveal internal mass distribution, and a spectrometer to identify minerals on the surface. Basically, it gave Vesta a full cosmic medical scan. And the results were immediate. First, the iron core is real. So that part of the theory was correct. Vesta really did go through planetary differentiation. A small body, with a planetary interior. That should have been the moment scientists felt relieved. Instead, things got worse. Because the second finding was far more complicated. The surface was a mess, not random, but layered in time. Old craters, young rifts, massive fault systems. Some regions even showed signs of resurfacing, like the ground had been reshaped after the fact. And that's where things stop making simple sense. Because a body this small is supposed to be cold and dead. No internal engine, no geological life. But Vesta looked like it had some history still unfolding inside it. Not erupting, not alive in a volcanic sense, but definitely not fully dead either. So a new idea started forming. Vesta isn't just debris. It's more like a scaled-down planetary experiment that never finished properly. And that idea changed the conversation. Because classic asteroid models are simple, cold, broken, inert. But Dawn suggested something more uncomfortable. Some small bodies actually went through real planetary processes. And it didn't stop there. Gravity data added another twist. Vesta's internal mass wasn't perfectly uniform. That means something disturbed its structure later on. In other words, it may have been reworked after forming. So now the question gets sharper. If Vesta fully differentiated early on, why does it still look so structurally inconsistent? Especially when you factor in that enormous southern impact basin, Rhea Silvia. You would expect an impact that big to destroy everything. Instead, it didn't. Yes, it carved a gigantic scar into the surface. Yes, it reshaped an entire hemisphere. But the core stayed intact. The structure survived. And that's where scientists hit a strange kind of wall. Because by all logic, a 500-kilometer body shouldn't survive that kind of event. It should have shattered into rubble. But it didn't. So the uncomfortable thought appears. Did we actually understand it, or did we just label something we don't fully grasp? Dawn left Vesta in 2012 and moved on to Ceres. But the data it left behind didn't close the case. It opened a deeper one. Now we know what Vesta is. The problem is, we still don't know why it is this way. And the more clearly we see it, the less simple it becomes. Sometimes, as the saying goes, the devil is in the details. And with Vesta, the details only make the mystery bigger. When you piece together everything we know about Vesta, one uncomfortable idea keeps coming back. It shouldn't still be here. Not in a poetic sense. In a physical one. Go back about 4.5 billion years. The solar system wasn't calm or organized. It was chaos on repeat. Collisions everywhere. Orbits still settling. Scientists often describe it as the prelude to the late heavy bombardment. Even before that peak around 3.9 billion years ago, impacts were already relentless. Honestly, it was less space and more cosmic bowling alley. And in the asteroid belt, things were even worse. Because this wasn't just a field of rocks. It was living under the influence of Jupiter. A planet so massive it contains more than half the mass of all the other planets combined. Jupiter didn't just sit there. It stirred the pot. It scattered orbits, triggered collisions, and kept the whole region dynamically unstable. So in theory, a 500-kilometer body like Vesta should have had three possible fates: get shattered, get absorbed, or get thrown out. And yet, it didn't. That alone raises a question: how? One explanation is simple geometry, location. Vesta sits in a relatively stable orbital zone, away from the most chaotic resonance regions. In other words, it stood in a part of the battlefield where the hits were less frequent. As the saying goes, wrong place, wrong time, but Vesta got lucky with both. Still, that only explains survival. not preservation. Then comes the second idea, Jupiter as a shield. Yes, Jupiter destroys things, but it also cleans house. It ejects incoming objects from the system and reshapes orbital traffic, like a rough cosmic security guard. Not gentle, but effective. This may have created pockets of relative stability in the asteroid belt, where fragments could survive longer. Vesta might simply be one of the survivors of that long gravitational filtering process, but even that doesn't fully solve it, because Vesta isn't just surviving, it's intact. And that pushes scientists toward a more radical possibility. Early in solar system history, orbital migration may have reshuffled everything. The NICE model, proposed in the mid-2000s, suggests that Jupiter and Saturn likely changed positions early on, destabilizing and redistributing small bodies across the system. If that's true, then the asteroid belt we see today is not original. It's a reassembled population. So Vesta might not have formed where it is now. It could have migrated. And that opens a deeper problem. If it moved, where did it come from? Closer to the Sun, farther out in the primordial disk? There's no definitive answer yet. And this is where the logic starts to strain. Because migration means everything has to be reinterpreted: its temperature history, its composition, its collisions. But rejecting migration leaves another mystery unsolved. Why does it look so structurally coherent in the first place? So scientists end up in a familiar situation. Every model explains part of the story. None explain the whole. And strangely, that uncertainty is what makes Vesta more important, not less. It's no longer just a surviving asteroid. It's a fragment of evidence from a chaotic system that refused to be fully erased. Which leads to a sharper question. If it didn't originate here, then where did it come from? And when all the data is combined, Vesta stops making sense in a different way. Not because we know nothing, but because what we know doesn't fit together cleanly. Three big problems keep refusing closure. First, where did the mantle go? Dawn mission data confirms differentiation. A metallic core exists. A crust exists. That part is solid. But the olivine-rich mantle, the middle layer, is strangely underrepresented. Even after a massive impact basin like Rhea Silvia, about 500 kilometers wide, the expected mantle material just isn't there in sufficient quantity. It's like cutting into a layered cake and finding the middle layer partially missing, with no clear explanation of who removed it. Second, the hemispheric imbalance. The southern hemisphere is dominated by Rhea Silvia, complete with a central peak rising about 20 kilometers. The northern hemisphere, meanwhile, preserves much older terrain. It's a dramatic split personality, one side heavily resurfaced, the other barely touched. For a body this small, that kind of asymmetry is rare and hard to explain cleanly. As the saying goes, it's like half the system got an update, and the other half didn't. Third, the impact history itself. Vesta shows multiple generations of cratering. Rhea Silvia is just the latest major event in a long sequence of collisions. But despite all that violence, the internal structure didn't collapse. It absorbed hits. It bent. But it didn't break apart. So the question shifts from what is it, to why didn't it fall apart? Individually, each issue can be modeled. Together, they don't fit. And that's why Vesta got a new label in planetary science. A protoplanetary relic. A half-finished world from the early solar system, frozen mid-process. Not debris. Not a planet. Something in between. A snapshot of formation that never reached completion. And that changes its role entirely. Vesta becomes a reference point. Earth is a finished system. Vesta is the draft version. By studying it, scientists can reconstruct early conditions: how short-lived heating from aluminum-26 drove rapid differentiation, how constant impacts reshaped fragile structures, and which parts of planet formation are inevitable, and which are just lucky accidents. But there's a deeper implication hiding underneath. If Vesta could form and partially survive in that chaos, what does that say about Earth's own early history? Because Earth's oldest rocks have been recycled again and again. Plate tectonics erased the beginning. We don't have Earth's birth record. But Vesta might be the closest thing to a surviving draft. Not a failed planet, more like a version of the early system that never got deleted. And that leads to an uncomfortable final thought. If Vesta is just one surviving fragment of early planetary formation, then are we looking at the final version of the solar system, or just the one that happened to survive the edits? The people who change the world usually just think one step deeper. If this story made you see things differently, hit like, subscribe, and save it. See you in the next story.